Hello there, MSTC, Algebra 2. I was just listening to some music on my planning period, and I was wondering if it would come out on the video, so that's what's happening right now. If you can hear it, anyway, that's all for the experiment. Just curious to see what would happen if music were playing. Anyway, back to 6.6. This is by far my favorite title of any section in the book. It's called Exponential Equations Solved by Brute Force. Amazing title, Brute Force. And the point is to figure out what x is in an equation like this, 4 to the x equals 87. You have solved a lot of different kinds of equations in your young lives, from linear to quadratic, but what has always been true is there's never been an unknown like x in the exponent position. You've never had 4 to the x. We've done some in class where they were nice even ones. Some of our quiz questions are ones that you could figure out without a calculator. This particular one is going to be brute force solved all on a calculator. So let me get my calculator out. I don't want a smart ink. No, I don't want a calculator. There it goes. And basically what you do is you narrow down the answer until you find what to the 4 raised to the what equals 87. And the instructions in my book say correct to 3 significant digits, meaning when we get this thing down to where the first 3 digits are not changing, we'll know that we're accurate enough. So first of all, let's just start narrowing it down a little bit. I know that 4 squared is 16, 4 to the third is 64. Oh, there's my ink again. I don't want you, ink. I want 4 to the, nope, nope. 4 to the third is 64, and 4 to the fourth is 256. So that tells me that this value of x is somewhere between 3 and 4, because 4 to the third is 64, 4 to the fourth is 256, which means that 87 is somewhere in between those, so x is somewhere between 3 and 4. So basically you just start narrowing it down. It's like kind of like playing 20 questions. You take a guess and see if it's too high or too low, and then you adjust your guess based on that. So I'm guessing that since 87 is closer to 64, I'm probably going to be somewhere closer to 3 than I am to 4. But this isn't a linear growth, it's exponential, so it's probably more in the middle than I think it is. It could even possibly be closer to 4, but I think it's probably not closer to 4. So I'm just going to guess a value and try to get closer and closer to my target of 87. So let's just try, if I can get rid of that ink. I don't want this ink. Okay, so let me try 4 to the 3.3, just as a starting place. Okay, and I get 97. All right, so that's too big. So now I've narrowed it down to 3 to 3.3, just whittling it away until I get an accurate enough answer. So I know it's less than 3.3. So how about 4 to the 3.2? That's 84. Remember, my goal is 87. So let's see. Here we go. We can see both. So let's see. I need to be between 3.2 and 3.3. So how about 4 to the 3.25? Just go right in between. And I get 90. That's too big, so I need to go less. 4 to the, how about 3.22? And you don't have to go right in the middle every time. Just narrow it down. Now that's pretty close. I'm 86.82. But that's a little low. I'm not at my desired accuracy yet. So I'm going to try 4 to the, let's see, I know I'm between 3.22 and 3.25, about 3.23. 88, so I'm between 0.22 and 0.23. 4 to the 3.225, that's between those two. Whoops. 4 to the 3.225. 87.4, so I need to be a little bit less. I'm 0.4 over right now. So how about 4 to the 3.222. 87.06. So now I'm getting real close. If I'm still a fraction high. So how about 4 to the 3.221? Okay, and I'm a little bit low. So I'm between 222 and 221, which would be 3.2215. You notice how we're adding decimal points. And that's pretty good right there. And what I'm thinking is I only need to be within 3 significant figures. And the one thing that's remaining constant at this point is it's going to be 3.22. Okay, so I'm not going to change my third significant digit. Even if I narrow it down further and further, I could get closer to 87. But 3.22 is 3 significant figures, and that's good enough. So my answer is 3.22. So I could write it something like this. X is approximately equal to 3.22. So by brute force, you have solved your first exponential equation. Now, you don't want to do that every time. So the next topic for the second half of chapter 6 is basically logarithms. This is a big day for you, your first exposure to logarithms. Some of you might have found them before, but basically what a logarithm means is it's like exponentiating backwards. All right, a logarithm means this. We all know that 10 squared is 100. So if I want to ask you that question backwards and say 10 to the what equals 100, then what I'm going to ask you is log base 10 of 100. Okay, log is a way to write an exponential backwards. It basically means what do I need to raise this base to get this answer? Okay, and with this first example, it's easy because we know that 10 squared is 100, so that's an easier answer to come up with. Some other examples, what is log base 3 of 27? Okay, so this is a tough transition for some people to make to ask this question backwards, but basically what this is asking is 3 to the what power equals 27, and that answer equals 3, because 3 to the third is 27. Now, you know how a lot of times in math problems we have stuff that's assumed, like if I write the square root of 9, I'm assuming there to be a little 2 right there. If I write x, I'm assuming that there's a 1 right there to be 1x. Stuff that happens most often, we don't write it every time. So what you need to know about logs, log of 1,000 is 3. I am assuming there is a little 10 right here. The base of a log is 10 unless otherwise noted. Okay, so log of 1,000,000 with no base written in, I assume it's 10, and that means 10 to the what equals 1,000,000, and that answer is 6. All right, so that's a short cram course on just what it means to be a log. It's just asking an exponential problem backwards. Instead of me saying, what's 3 to the 4th? And you say, well, 3 to the 4th is 81. I should probably write this. What you've already learned how to do is, what's 3 to the 4th? And you say, 3 to the 4th is 81, because 3 times 3 times 3 times 3 is 81. Instead, now I ask, what's log base 3 of 81? And I'm asking it backwards. What do I need to raise 3 to get 81? And that answer is 4. It just depends on what's the unknown and what's the known. Okay. So let me show you another, here's really where logs come into play. When you have an equation where the exponent is your unknown, like, let's see, 10 to the x equals 0.005. Okay? Here's how you might choose to remember this, and some of you cat lovers might not like this very much, but imagine our unknown here is the exponent, and it's stuck up in the little perch. It's like up high on an elevated position, like a little kitty cat stuck up in a tree. You know, and there are different ways to get a kitty cat out of a tree. You could call the fire department. You could get a ladder and climb up there. You could do lots of stuff to get a kitty out of a tree. But one really effective way is to get a big log and knock the kitty out of the tree. So imagine your unknown in the exponent spot as a little kitty in the tree. And the way you're going to get it out of there is to use a log. In other words, we're going to take the log of both sides of this equation. All right, the basics of algebra says if you do something to one side, you do it to the other. So I'm going to take the log of both sides. Now, the reason that you use the log to get the kitty cat out of the tree is because this side over here is log base 10, that 10 is understood, of 10 to the x. And that's saying, what do I need to raise 10 to get 10 to the x? If you think about that sentence, I hope that it pops into your head. This side is now just x. All right? The exponentiation process and the logging process cancel each other out. Just like if I had x plus 2 equals 4, I would minus 2 on both sides because plus and minus cancel each other out. Just like if I had the square root of the square root of x equals 4, I would square both sides because squaring and square rooting cancel each other out. Okay, logging and exponentiation cancel each other out. Therefore, the log base 10 of 10 to the x is equal to x. And on this side, I'm left with log base 10 of 0.005. Okay, and this is not something you should know. You should know what log base 10 of 100 is because 10 squared is 100. But 10 to the blank equals 0.005 is not a nice, neat number. So what we need to do is log of 0.005. On your calculator, here's log, and it's understood to be base 10. So we just put in 0.005, and this will be our answer, negative 2.301. Let's just call it negative 2.301. So what's new for you here is this step right here, logging both sides. I can't stress enough, you need to know when the unknown is in the exponent position and you need to get it out of there, you're going to log both sides. In a sense, what happens is this 10, when you log both sides, or excuse me, this x comes out to the front, and you're left with log base 10 of 10, which is 1, because that's saying, what do I need to raise 10 to get 10? And that's 1, and the only thing left is the x. So that's an example that has 10 in the base. Let me do one more quick example for one that does not have 10 in the base, like 8.09 to the 5x is equal to 40,800. Okay, so you approach this equation, you say, well, I've got an unknown in the exponent position. I know how to get rid of that. I'm going to get rid of that with a log. So log both sides. Make sure you do both sides. Okay, the reason you do that is because taking the log to the little kitty cat frightened in the tree, very gently and nicely, of course. I wouldn't have never support cat abuse, but it gently removes the cat from the tree, and we get 5x times the log of 8.09 equals the log of 40,800. Okay, another thing I want to stress to you is that the log of 8.09, this is some number. Okay, I don't know what number it is. It's whatever I need to raise 10 to get 8.09. So it's some value a little bit less than 1, because 10 to the first would be 10. So this number is what I need to raise 10 to get 8.09. Same thing over here. This is some number. So I don't know exactly what that number is. My calculator could tell me, but before that, if you had this equation, you would just, if I had 5x times some number, you could do whatever order you want. You could divide by 5 first or divide by log 8.09 first. I'm just going to kind of group the 5 and the log 8.09 together. And since it's just a number, whoops, 1 extra 0. Since it's just a number, I can divide both sides by it. I'm going to divide by 5 log 8.09, 5 log 8.09. The reason I chose to divide by that is because I'll cancel it all on this side. And x equals all of this stuff, which is log of 40,800 divided by 5 times the log of 8.09. All right, so let's see what that is. Log, no ink, don't want you ink, log of 40,800 divided by, parentheses, 5 times the log of 8.09. And close that second set of parentheses and enter. And I get 1.01. All right, 1.015, or I'm just going to call it 1.02. Okay, so when you solve any equation, you should always double check your work. So do 1.02 times 5, plug it in up here, times 5, and do 8.09 to that, and make sure you get 40,800. So 8.09 to the 5 times 1.02, 8.09 to the 5 times 1.02 should be 40,800. Now I rounded off my 1.02 quite a bit. I think it was actually 1. Oh, there it was right there, 1.01. Let's see, 8.09 to the 5 times 1.01562, 1492, and that's a lot closer to 40,800. So there you go. This is your intro to logs. They mean the opposite of exponentiation, and they are used to solve equations whose unknown is in the exponent position. All right? So it's a happy day. Be glad you now know what logs are. We will talk about these things for pretty much the rest of this chapter. It's a long chapter, 14 or 15 sections, and then we will have a test on the whole exponential log thing. All right, so I hope you enjoyed logarithms. I will see you in class. Have a lovely evening. Young out.